Hi, and good day to everybody. My name is Dardan, and I will chair today's session on power electronics. I'm with the University of Pristina in Kosovska Mitrovica, and it will be my pleasure to share this time with you. The first presenter for today comes from Bulgaria, and he is Professor Nikolay Hinov. I hope he is here. And
hello, I will present instead of Mr. Hinov. I am the co-author of this paper.
Okay, Tsveti, Hranov, you're welcome. You will the first paper in this session today is practical approach for improving the dynamics of the resonant DC-DC converter. Please take your time and present your work.
Okay, I will share the screen. Do you hear me good?
Yeah, of course.
Okay. So now can you see the presentation?
Yeah, presentation is shared.
Okay, so I will start it. So my name is Tsveti Hranov, and I will present the tolerance analysis of common transistor DC-DC converters. I am co-authoring this paper with my colleague Nikolay Hinov. Brief introduction. Tolerance analysis is made on the most widespread converters. This is the buck boost and buck boost converters. And the idea is to observe the change of the parameters of the reactive elements upon the state variables, that is the current through the inductance and the output voltage. The results are obtained, which are visualized as characteristic and presented on 3D graphs. And this study is interesting in view of the operation guarantee of the performance of power electronic devices. So this is the study. We have a common mostly output parameters such as output voltage, output current. We are using the same duty cycle, operating frequency 300 kilohertz, and the filter elements are the same with the given tolerances. For the inductance, this is plus minus 20% and for the capacitor, this is plus minus 10%. So in order to obtain the comparable results, the operation of the converters are at maximum the same. This is achieved using the following input voltages. For the buck converter, this is 40 volts. For the boost, it is 10 volts. And for the buck boost, it is 20 volts. And initially, the results were obtained for the influence of the tolerances in the steady state and then on the transient and dynamic processes. So these are the results for the buck converter. Here can be seen the inductor values, that is plus minus 20%, and the capacitor values plus minus 10%. And this is how the average RMS inductor to the inductance of the converter is changing. Same here for the maximum capacitor voltage from the tolerances. The next slide shows this for the boost converter. As you can see, the graphs are a little bit different, but the idea is the same to see how the tolerances are affecting on the steady state. And here is the buck boost converter tolerance analysis. Again, it can be seen how the tolerances of the circuit elements are affecting the steady state operation of the inductor current and the capacitor voltage. And here are the results for the transient processes. First, again, for the buck converter with the inductor current and output voltage at different pairs of inductance and capacitance. This is the nominal regime here, purple. Here is for the boost converter. And lastly, for the buck boost converter, of course, the output voltage is inverted because this is an inverting topology. And I can summarize the results with the following statements. The change of the operating mode due to the tolerances of the filter elements is insignificant in steady state mode, but on the other hand, the transient process is significant and different in the different topologies, and due to the nature of the operation of these converters, serious attention should be paid to the synthesis and control of the the setting of the control in order to achieve improved characteristics and guarantee the output performance, like systems for soft starts and others. The manuscript presents a model-based approach for tolerance analysis of the most common used basic power circuits. This is a good approach for the design to evaluate the values of the circuit elements and parameters of the operating modes, what changes can be expected in them due to tolerances, and how to make optimal selection of elements by various complex indicators such as price, quality, reliability, etc. And the achieved results are useful for improving the practical training and studying in the converters in general. This project is supported by the European Regional Development Fund with the Operational Program Science and Education for Smart Growth in the National Center of Mechatronics and Clean Technologies in Bulgaria. Thank you very much for your attention.
Thank you very much, dear colleague Hranov, for your presentation. As I can see, chat is currently empty. We do not have question. Any question for Mr. Hranov from other participants? Okay. You will have just one question from me.
Okay.
I read this paper in meanwhile, and just about applicability of it. Did you apply this DC-DC converter somewhere in practice?
Yes, we have made some studies using real converters, and yes, we obtained similar results. However, we will continue to do experiments with different manufacturers of inductances and capacitors in order to obtain more practical data and compare it with the theoretical results that we achieve.
Because in the title and in a few places in the paper you wrote the improving of the dynamics of the resonant. You mean you improve the performances, how to say, during the operating time, or somewhat different?
At the design stage.
Design stage.
Yes.
Because this kind of title and topic is very rare to have improve of dynamics. What is just one question about that? I have no more questions. Thank you.
Okay, thank you.
The next presenter comes from Slovakia, and the title of paper is Design of a Wireless Charging System for Inverter. And this paper will be presented by Michal Frivaldsky. Are you here, dear colleague? I will repeat my call.
Probably he is not.
He's not here.
Yes.
Maybe time zone, like in my case, because always we are thinking about the Central European time, and I was already prepared nearby the computer, but
Okay. Okay. Maybe he will join later, so he
yeah,
will
of course.
make presentation after all.
Yeah, we will give the opportunity to the next presenter to take this time. Next paper is a 5 volt to 180 volt charge pump for capacitive loads in a 180 nanometers SOI process. This paper will be presented by Jakob K. Toft. Mr. Toft comes from Denmark. Are you here, dear colleague?
Yes, I am.
You're welcome. Take your time and present your paper. We have, I think, enough time. For each paper is 15 minutes reserved, but you saw for the first presenter was so quick.
Yes.
Welcome.
Thank you. Yes, so this is some work that is built upon the previous presentation I gave on the optimal topologies for the same application. And again, I would like to start by introducing the background for my project, the use charge pump topology. Let's see, I haven't gotten this updated. Embarrassing. I will just continue. So again, it's a MEMS microphone application where the sensitivity is given by the bias voltage over the air gap times the change in air gap per change in pressure. And the application is still the MEMS microphone where the power consumption is limited to 20 microwatts. There is limit has increased to half a square millimeter due to some supporting circuits that will be introduced later. And the clock frequency of the circuit has to be at least 100 kilohertz or above to reduce the risk of interference with the audio measurements. And the rise time must be less than 10 milliseconds. And the load is a MEMS structure that has a capacitance of 10 picofarads and a leakage of 2 nanoamperes at 180 volts. So in the previous presentation, the study showed that the Pelliconi topology was optimal to reach these just 180 volts from a 5 volt supply using a little area and little power. However, in this work, I have used an extension to the Pelliconi topology where the transistors in this diagram M5, M6, and the capacitor C bulk has been added to stabilize the bulk voltage of M3 and M4, as that leads to some problems in the traditional Pelliconi topology when you scale it with a lot of cascaded stages. So the voltage gain is given by the voltage supply times the voltage supply plus the number of stages times alpha, where alpha is the ratio of pumping capacitance to pumping capacitance plus the parasitic capacitance, where C pump corresponds to the capacitance of C1 and C2, and parasitic capacitances are the parasitic capacitance on the top plate of the capacitors, this node and this node. And the voltage gain can be maximized by maximizing the pumping capacitance or minimizing the parasitic capacitance, where maximizing the pump capacitance requires a lot of area because you need to use larger transistors, and this works against the target of having a small charge pump. And minimizing C parasitic requires that the topology is kept simple and utilize small transistors, which is what this topology has achieved in terms of optimal. So on a system level, the entire system consists of a clock generator that generate the clocks A and B for the charge pump, high voltage ESD protection because we have 180 volts here, and then an output filter to remove noise from the generated bias voltage before the bias voltage is put on connected to the MEMS. The clock generator is based on a structure known from 911 clock generators, but in this implementation, the delay chains are sized to create a crossing clock, where the clocks A and B, they cross the mid supply. This reduces the amount of reverse currents that are in the topology, normally in literature, people refer to using a non-overlapping clock, but using a non-overlapping clock results in a lower voltage gain. The charge pump itself was designed to minimize the size of the pumping capacitors to maximize the voltage gain and minimize the parasitic capacitance of transistors and layout, and to compensate the reduced voltage gain by adding additional stages. So I implemented two variants, a variant where 75 femtofarad capacitor was used for C1 and C2, which required 57 cascaded stages. 75 femtofarads was the minimal feasible pumping capacitance, and the capacitance below this had diminishing returns in terms of area. And then I implemented the 300 femtofarad variant, which only required 46 stages to reach 180 volts from the 5-volt supply. And that was implemented to have something to compare the minimum size implementation with. All the transistors were implemented using minimum size transistors, as the on-resistance was low enough, and using minimum size reduced the parasitic capacitance and maximized the voltage gain. And then layout, a significant amount of area was spent on spacing wires and capacitors to further reduce the amount of parasitic capacitance. The output filter is implemented as two RC filters, while the resistance is implemented as a diode-coupled PMOS transistor, because as the voltage settles, the voltage drop across the transistor is very low, and the impedance become very high. The cross-coupled diodes are used for ESD purposes. So a ESD discharge can go through the diodes that are larger than the transistor. And the ESD protection itself is implemented using stacked PMOS transistors, and is based on blocks provided by the design kit. And I implemented 3 different versions of ESD to investigate the impact of leakage through the ESD. One version has leakage of 10 picoamperes at a voltage of 210 volts on the high voltage node. Another version has a leakage of 10 picoamperes at a voltage of 285 volts. And then I also implemented a version of a charge pump where no ESD was used, which is risky, but that way leakage through the ESD structure is eliminated. The physical implementation was fabricated in a 180 nanometer SOI process with a 200 volt breakdown voltage from transistors down to the substrate, which is implemented by using buried oxide and deep trench insulation. The transistors used for the charge pump itself is only rated for 5 volts, but the breakdown voltage down to substrate is 200 volts. Yep. The physical area of the different variants and ESD versions is listed in this table, where the 300 femtofarad charge pump is a little more than twice as big as the 75 femtofarad charge pump, while the charge pump is only the cascaded stages and the clock generator. The ESD area is significant with 0.1 square millimeter approximately, and the output filter is even larger with almost 0.15 square millimeters. So both the filter and ESD contribute significantly to the total area of the charge pump implementations. Only one implementation could not fit on 0.5 square millimeters, the 300 femtofarad version with the large ESD structure. But all of the others fulfilled the requirement of fitting on less than half a square millimeter. To measure the charge pumps, I used a source meter to set the load to a fixed 2 nanoamperes for uniform measurements, and I used an amplifier with a very low input bias current to buffer output for oscilloscope measurements, such that the instruments did not load the charge pump in any significant way. The buffer has a input bias current of 250 femtoampere, so significantly less than the 2 nanoampere synced by the source meter. So the output voltage and power consumption of the different charge pump variants and ESD versions is listed in this table, and all implementations managed to reach above 180 volts from the 5-volt supply when they're clocked by a 2 megahertz clock. The power consumption on the other hand, though, is significantly more than the 20 microwatts that was the target, where the 75 femtofarad version consume 330 microwatts, and the 300 femtofarad version consume 620 microwatts. Comparing the two charge pump variants with simulation results revealed that the 300 femtofarad charge pump is less sensitive to parasitics compared to the 75 femtofarad charge pump, as expected. When simulations are run without the parasitic extraction, the output voltage difference for the 300 femtofarad version is only 20%, whereas it for the 75 femtofarad charge pump is 30%. So the 75 femtofarad variant is more sensitive to parasitic capacitances than the 300 femtofarad variant. Looking at the output, the power delivery capability of the two charge pumps, it can be observed that the 300 femtofarad variant can supply almost 3 times as much power as the 75 femtofarad version, 80 microwatts versus 240 microwatts. But even though the 300 femtofarad charge pump can deliver more power, it cannot reach a higher output voltage than the 75 femtofarad charge pump. So the problem is not about delivering power to the load, but about parasitic capacitances, reducing the voltage gain of the charge pumps. Rise time of the two variants when clocked at 1 megahertz, the 75 femtofarad variant doesn't rise fast enough. When clocked at 2 megahertz, it does, which is perfect, except at this clock frequency, the power consumption is way too large with 300 microwatts for the 75 femtofarad version. But reducing the clock frequency reduces the power consumption, but unfortunately also affects the output voltage of the 75 femtofarad version. For the 300 femtofarad version, the clock frequency can be reduced to 100 kilohertz and it still can output more than 180 volts, whereas the 75 femtofarad version drops down to 178.5 volts. But running the 75 femtofarad version at 100 kilohertz reduces the power consumption to just above 20 microwatts. So one approach to operating charge pump could be to use a 2 megahertz clock during startup to achieve the short rise time, and then reduce the clock frequency after reaching 180 volts to save power. Comparing with the prior art, the implementations of this work there are charge pumps in prior art that have a higher voltage gain and higher output voltage, but they also have an area that is 200 times larger than the charge pumps implemented in this work. And the second highest output voltage in literature does not reach 180 volts, while still consuming more than 40 times the area of these charge pumps of this work. So the developed charge pumps is reaching a goal that no prior art has reached, but the application is also different than for what prior art has sought to achieve. So in conclusion, with regard to the design target, the implementations got close. The 75 femtofarad variant area was less than half a square millimeter. And at a clock frequency of 2 megahertz, both charge pumps had a rise time of less than 10 milliseconds. But the power consumption at 2 megahertz was much higher than the target of 20 microwatts. But lowering the clock frequency after having reached 180 volts during startup could reduce the power consumption to 40 microwatts for the 300 femtofarad version and 20 microwatts for the 75 femtofarad version. So in short, the two charge pump variants illustrated the impact of parasitic capacitances, as the larger pump capacitance required fewer stages to reach 180 volts, and the 300 femtofarad variant was less impacted by parasitics when comparing simulations and measurements. And although the 75 femtofarad charge pump variant has a lower voltage gain per stage, it used less area and consumed less power than the 300 femtofarad variant. Often in the literature, people are talking about maximizing the voltage gain per stage, but this that would not have been a suitable design approach for this application. So for this application, in terms of both power and area, the best approach was not to maximize the voltage gain, but to compensate by adding additional stages. So, thank you.
This is also my question. The dear participants, do you have any question for Mr. Toft related to this good presentation? It seems you will stay without questions from colleagues. But I will say a few words about your work. Work is good, supported by experiments. You presented it is in the best possible way. And thank you for this very nice presentation, dear colleague Toft.
Thank you.
The next, you're welcome. The next presenter comes from China.
Excuse me, good afternoon. My name is Jakub Skorvaga and I came to replace Michal Frivaldsky.
Okay, the second paper, author of the second paper in this session. You are here?
Yes.
Okay, welcome.
Thank you.
Now it will be my pleasure to introduce colleague Jakub Skorvaga.
Yes.
And he will present the paper Design of a Wireless Charging System for e-Scooter. The author comes from Slovakia and will present now his work. Welcome, please, take your time.
Thank you. Okay, so hello to everyone. My name is Jakub Skorvaga and my presentation deals with the design of wireless charging system for e-scooter. The aim of this research was to design and construction wireless charging system for electric scooter. This research was created as a cooperation with my colleagues Michal Frivaldsky and Miroslav Pavelek. This research included the design and construction of couplers for the implementation of wireless power transmission and also the choice of the suitable power electronics topology. The motivation of this research was the removal of disadvantages associated with using of standard charging module, for example, risk of water interaction, connector oxidation, and low charging power and long charging time. Our proposed system is designed for, our proposed system is designed for e-scooter Xiaomi Mi 365, which is a very popular e-scooter on the market. This e-scooter contains a lithium-ion battery with a capacity of 7.8 amp hours and consists of 30 cells. The voltage of one cell is 3.6 volts, and the commercially available charging module has a power of 71 watts and an output voltage of 42 volts, while it is able to supply a current of 1.7 amps, and it takes 5 hours to charge the battery with this commercial adapter. Design of coupling elements. For design of couplers, we use software designed for design of wireless charging systems. for a successful calculation, it was necessary to enter the input parameters into the graphical interface of the software. These parameters include output power, load volume, required efficiency, transmission distance, and also nominal switching frequency. In this slide, we can see a simulated curve of the coupling coefficient depending on the distance of the coupling coils. Below this curve are calculated values of the coils, compensation capacitors, and also the values of the parasitic resistances of coils required for transmission of 200 watts power. Next, we adapted the shape of the coil to the shape of the base of e-scooter, and it is an oval coil inserted in a rectangular plate. The board is complemented by ferrite shielding, which increases inductance, and the simulated inductance value in the console program was 92.6 microhenry. With the use of designed PEM console model, the evaluation of the magnetic radiated field according to standards was realized, and the operation was considered for nominal power 200 watts, while the distance between coupling coils was set to 50 millimeters. And in the picture, we can see the distribution of magnetic field within the proposed wireless charging system, where border of the amplitude is set to 27 microtesla, what is maximum exposure limit defined by international standards. From the simulation, you see that the magnetic induction drops below the limit approximately 0.2 meters from the system within radial or axial direction. The designed model is made using a 3D printer. The experimental model consists of 17 turns. The length of the board is 42 centimeters. The width of the board is 14 centimeters, and with ferrite shielding, the measured inductance value of the model was 91.6 microhenry. Implementation of compensation capacitors. The value of the capacitance of the compensation capacitor was obtained on the basis of the Thomson relation. The capacitor consists of 14 series pairs connected in parallel, and the resulting capacitance of the compensation capacitor was 39.2 nanofarads. Sorry, in the picture you can see the experimental model. Power electronics concept for proposed e-scooter system, charging system. The wireless transfer is realized here with a reduced voltage, while secondary side uses a high frequency, low voltage Schottky rectifier, followed by buck type of DC-DC converter, operated with constant voltage and constant current charging mode. The concept contains up to 7 subsystems, which make it a more complex system in terms of the number of components. But on the other side, the charging control algorithm is much simpler. Following converters was calculated and designed in this manuscript. So included power factor corrector, primary side DC-DC buck converter for reducing input voltage, full bridge inverter, and secondary side rectifier, and also the secondary side DC-DC buck converter for charging battery module. The picture, we can see the experimental model of voltage inverter. Experimental verification of the functionality of the proposed solution was performed by laboratory measurement. The measurement to obtain the dependence of efficiency on the size of transmitted power was performed for 3 different mutual distances. In the picture, we can see the laboratory measure setup. Here we can see the results for measurement of efficiency. At the distance 5 centimeters, the maximum efficiency of 92.5% was achieved at the power 160 watts. At the distance of 6 centimeters, the maximum efficiency was achieved at 81% at the power of 125 watts, and the highest efficiency at the distance of 7 centimeters was 80% at an output power of 2 watts. The table in the second part of the laboratory measurements, focus was given on the investigation of efficiency and voltage gain characteristic depend on the operational frequency. The measurement was performed for a total 16 switching frequencies. The range from 70 kilohertz to 105 kilohertz. And the highest efficiency, 99.5%, was coupling coil was achieved at the distance 50 millimeters and frequency of 95.5 kilohertz. Simultaneously, at this point, high voltage gain is achieved. At the 60 millimeters, the maximum efficiency was 85% at the frequency of 90 kilohertz, and the value of the voltage gain also reaches its maximum. At 70 millimeters of distance, the efficiency of 90% was achieved at a frequency 87.6 kilohertz, and here the voltage gain is not reaching its maximum, but opposite to previous situations, it is a little bit higher, thus enabling to transfer more power, but for the sake of the reduced efficiency. And conclusion, in this research, we managed to achieve the goals summarized in the points. So choice of the power electronics topology and design of power converters, proposal of coupling coils with respect to the dimension of the scooter, construction of physical model coupling coils and capacitors, and also power converters, and experimental verification of the proposed solution by laboratory measurement. Thank you for your attention.
Dear colleague Skorvaga, thank you very much for your presentation, and it was very interesting. And dear colleagues, do you have any question for Mr. Skorvaga? It seems and chat box is empty. We do not have questions from colleagues, but I will ask you a couple of questions.
Mm-hmm.
For example, I read the paper and I didn't saw any real photo of this e-scooter. What is an e-scooter? Do you have any photograph of it?
No, so far we just make tests on the converters in laboratory without the e-scooter. So maybe in the future we can try to make some tests on the real e-scooter.
Because it's always interesting not to see just research results and some practical devices to have in paper. And the second question is, do you think about power to develop a charging system of higher power?
I don't know if the battery are able to receive more power, because we were limited by charging current of the battery pack of the e-scooter. So maybe when we use batteries with higher charging current, we also can try to charging with higher power.
You said in your paper that how to say, your technology of charging, wireless charging, is very well known, but I still have my laptop and phones charging in traditional way by a cable and adapter. Okay, Mr. Skorvaga, thank you very much for this nice presentation
Thank you.
and sharing your research results with us. The next presenter comes from China. Shuaibu Musa Adam will present the paper soft modeling of photovoltaic modules based on MATLAB Simulink. Are you here, Mr. Musa Adam?
Previously it was connected, but yes, it is.
Yeah.
But do not react.
Cannot find. Oh yeah, I see him here. Do you hear us, dear colleague Adam?
Maybe we can go with next one. Okay, maybe
Okay.
he will.
Hello.
You are here. Welcome,
Yes,
please.
I'm here.
Take your opportunity to present your work, and in next 15 minutes, present your research results. Are you here, Mr. Adam?
Yes, I'm here, sir.
Share, please, your screen and
Okay.
start presentation.
Hello.
Yeah,
Yeah, can you see my screen?
yeah, we see it.
Okay. Good evening, all distinguished guests present. I am Shuaibu Musa Adam, presenting our collaborative research study on the topic soft modeling of the photovoltaic modules based on MATLAB Simulink. The presentation is going to be made based on the following outline. So, introduction, motivation for the study. A large volume of PV panels modeling technique exists in the literature. However, majority of the technique use some arbitrary or assumed values of the IV equation parameters, which consequently affects the accuracy of the overall parameters estimation. And the effect is more prominent in methods which employ iterative approaches due to sensitivity of the initial guess values, which consequently affects or leads to the convergence problems for the models modeling. As such, the current study focused on using MATLAB programming to implement the PV modules in the MATLAB Simulink. The proposed algorithm in this study uses the manufacturer's datasheet information to implement a 5-parameter single diode model of the PV module. As you can see in figure 1, it's shown the circuit, the equivalent circuit of the single diode PV model of the PV module device used for the implementation of the algorithm. Why the single diode model? The single diode model was used because of its easy implementation, fast convergence, less complexity, as well as its suitability for majority of the circuit simulators. Now, the mathematical model of the single diode model PV device used. As you can see, equations 1 to 4 show the AB equation parameter from the basic theory of semiconductor. In figure 2, you can see the IB curve characteristic of the PV device at standard test conditions. On this figure, you can see 3 highlighted critical or important points on this curve, which are ISC, the short circuit current, VOC, the open circuit voltage, and the MPP, that is the maximum power points of the IB curve characteristics. Now, the manufacturer's datasheet information. In this study, 3 model manufacturers or 3 different types of PV modules were used to test the proposed algorithm. And these are the datasheet information for these 3 tested PV modules, which are all from the crystalline silicon family. Now, the methodology. The methodology for this research study was categorized into 2. 1, the IB equation parameters were derived. Secondly, the derived parameters were used or were implemented in the MATLAB M-file script in order to test the proposed algorithm. As you can see, the 5 unknown parameters, which are the light generated current, the reverse saturation current, the diode ideality factor, the series and shunt resistances of the PV modules were derived using equations 5 to 8. Now, the methodology. After the parameters were derived as shown in the previous slide, they were implemented using the M-file script as shown in this iterative algorithm flowchart. Newton-Raphson technique was used for the algorithm implementation, as you can see. Similarly, a Simulink model of the proposed algorithm was also developed in the Simulink environment of the MATLAB, in which all the 5 IB equations parameters were also designed and implemented similar to the one shown in the M-file scripts in the previous slide. Now, as you can see on this screen, it shows the PV model subsystem of the Simulink model. This subsystem can be used to test any of the PV model in which the 5 unknown parameters were derived. So this shows an improved Simulink model for the SolarX MSX60 PV model. Now, the results and analysis. It can be seen from tables 4, 5, and 6 on the next slide that the implemented model correctly matched with the experimental data obtained by the manufacturers at STC based on the analyzed parameters. On table 4, you can see some highlighted values of the maximum power P max E and the maximum power P max M. The maximum power P max E shows the maximum power obtained by the model parameters, that is the experimental maximum power. Meanwhile, the P max M indicated the maximum power obtained after the proposed algorithm has been run. It can be seen that that these values correctly match with the one obtained by the model manufacturers. Figure 6 also shows the adjusted parameters, the result obtained for the adjusted parameters of Solaris MSX60 PV modules at STC. Similarly, the Pmax-E and the Pmax-M coincided. Meanwhile, the values of the light generated current IL has also been bolded, which also is similar to the values of the short circuit current ISC. So in this study, you can see that the IL and the ISC are not exactly the same, which disproved the previous assumption by researchers that the short circuit current and the light generated current at STC are exactly the same. However, on this study, we found out that they are entirely different. It can be seen from table 7 that the diode ideality factor were compared for the 3 tested models, which can be a comparison of this ideality factor shows that the values differ from one another, despite that the models are all from the same family group, which clearly shows an improvement in the previous researchers, in which they assumed the value of the diode ideality factor to be exactly the same. It can also be seen from table 8 that the modeling algorithm yielded accurate results as expected, with crystalline silicon CHSM P220 having the best match values with the least power error measurements. Now, the compared IB curves for the Solaris MSX60 module. The solid blue lines in the graph indicated the experimental output, while the dashed red lines represent the adjusted parameters output. As can be seen, the IB curve from figure 6 and the PB curve from figure 7 of the adjusted and the experimental data successfully coincided at the 3 critical points of these curves for the Solaris MSX60 module and all other tested modules for this study. Now, the continuations of the results. Model validations. The proposed algorithm has also been validated by testing this algorithm at different irradiance and temperature. As you can see, figure 8 shows the values of for the Solaris MSX60 PV module at selected irradiance, while figure 9 shows the value of the same PV model at selected temperature. The results obtained clearly show an improvement of the result obtained by some previous researchers as cited here, using the same PV model but with different modeling approach. Those validate the proposed modeling technique performance at conditions different from the STC. Now, conclusions. The proposed algorithm used manufacturers' datasheet information to implement the single diode PV module, in which the use of arbitrary values of some of the IB equation parameters were dismissed or were abolished. However, the algorithm proposed meets the key features of minimal or negligible differences between the model and the actual measurement data, most especially at the maximum power points, while exhibiting a fast convergence. It has also proved to have improved the result obtained by previous study using similar approach, but with different initial guess values. Now, prospects for future work or for future studies. The validation of the proposed modeling technique using the real outdoor experimental data is beyond the scope of the current study. As such, it is suggested that it should be part of the future studies objectives. Meanwhile, the proposed method considered the use of single diode model for implementation simplicity. It is also suggested that double diode model can be used for further improvement of the current techniques. However, it should be borne in mind that this may require advanced and complex programming. Thanks. Here are some of the selected references from this study. Now, the modeling algorithm. The algorithm was simultaneously implemented in MATLAB R version R2020A, running on both a MacBook and a Lenovo laptop PC. Thanks for listening. Have any questions, you can ask.
Thank you, dear Mr. Musa, for this nice presentation. Any question for colleague Musa? Chat is empty. Okay, I will ask you one question.
Okay.
Yeah. Could you please show once again this slide with the conclusions?
With what? With
last
sorry?
one. Before, thank you for your attention. The last one.
The last one, right?
Yeah, the last one. Just one question about this, the second conclusion. You said difference between modeled and actual measurements data. You have used manufacturers' data sheets as measurement data. Have I right or no?
Yes, the manufacturer's data is the actual measurement data.
Yeah. Yes, I saw you got a very nice agreement between results. Is your program code that you developed in MATLAB available, or just for your purposes?
Sorry? Yeah, it can be available. Yeah, it's available and it can be shared.
Available. Okay, yeah. Thank you. That's all from my side.
Yeah,
thank you very much, dear Mr. Musa. The next presenter is Dan Salisteanu, and he comes from Romania. The paper is 3-level inverter, control techniques, design, analysis, and comparisons. Are you here, colleague Salisteanu?
Yes, dear professor, thank you very much.
Welcome, please. Take your time and present your research results.
I hope that my presentation is visible now.
Yeah, you shared the screen with us.
Thank you. This paper was written by the authors from the University of Craiova and from the Research and Development Department of company Inverter Craiova, with many products in the field of power electronics. The outline of my presentation is as follows. After a short introduction, I will present the inverter control simulation schemes. After that, a short discussion about the control laws design and tuning. In order to assess the performance, the quality evolution of the inverter system, I will present some criteria. And the main part of the paper is related to the simulation results and comparisons. In this work, we address design of control techniques for inverters. The multi-level power converters are, as you know, main elements of high voltage electric drive and power supply systems. In order to obtain an accurate control system, it is very important in the first stage to use simulation and specific computer-aided design tools. So in this work, a detailed software model of a 3-level inverter is designed and then used in order to test some control techniques. These control techniques are integrated in the form of PID controllers, and we used some tuning methods in order to obtain the optimal parameters in 2 specific simulation cases: a multi-level inverter with a linear load and respectively with an asynchronous motor load. And as you will see, we have analysis and some comparisons of the quality criteria. Regarding the inverter control simulation schemes, it is very important to have such inverters because they are requested by the market for several industrial applications. And in this context, we have a collaboration, our university, with this company in the Eltra Craiova, and we intend to design a prototype of this 3-level inverter. We designed software model with some main parts, such as a 3-level power inverter in neutral point clamped topology, the load, which is a linear load and asynchronous motor, the pulse width modulation command block, and the control loop. In the case of linear load, the controlled variable is the output voltage. And for the load with the induction motor, we have as control variable the motor speed. Of course, according to the strategy of a constant ratio between voltage and frequency. And in this figure, you can see the software model developed in MATLAB Simulink. And the main blocks are the pulse width modulation command block, the power 3-level inverter, the load. Here the load is the asynchronous motor, but in the second simulation case, we will use a 3-phase RL load. And in the lower part of this diagram, we have the implementation of a classical PID controller with a lot of blocks, with saturation, and so on. And of course, we have here a lot of measuring block, output voltages, some step sources, and scopes for the main variables. In figure 2, you can observe 2 important diagrams. The diagram of the pulse width modulation command block and the 3-level neutral point clamped power inverter. These 2 blocks are linked via the command signals for 12 IGBTs in the inverter legs. And it is important to see that the fundamental harmonic of the inverter output voltage in time domain is obtained as in figure 3 by using a numerical low-pass filter. In this simulation model, we build a software model with a lot of improvements. For example, we used the real switches with proper snubber elements. We use the continuous time domain integration with the variable step. We use saturation blocks for the PID controller. In section 3 of this presentation, I will present you some issues about the PID controllers. These, of course, these proportional integral derivative control laws are well known. And here in the equation 1, 2, 3, 4, and 5, you have the main relations concerning the transfer function of these PID controllers with some main parameters of design, such as proportional gain, integral gain, derivative gain, and of course some time constants, such as reset time and derivative time. These controllers are very good, but in order to implement these PID controllers in practice, we need the values of the parameters. And we can use, for example, some tuning methods when we know the model of the process, such as Opelt, Kopelovich, Pesant, and so on. But of great importance for inverter control are the heuristic methods, because we don't have a full mathematical model of the inverter. So we can use some tuning methods which can be applied without the knowledge of the plant model. And in our work, we used three tuning methods: Nichols, Ziegler-Nichols, and Hokushin method. For example, in table 1, you have the value of the control parameters for Nichols method. And in the paper, you can see also the other two methods. In section 4, we discuss about the quality criteria and performances for control system, because it's very important not only to close the loop, but also to assess the performances of our control systems. And usually you can use two types of criteria: global quality criteria. These are integral or summation criteria given by the general relation 6. And usually they are expressed in these forms of integral errors. In equation 7 to 10, you have all the 4 integral errors used in our study. Of course, from the engineering point of view, many times it's easier to calculate, to compute the local quality criteria, such as position gain coefficient, the position state error, and of course, other local quality criteria. In figure 4, you have the classical form of a closed loop system with the transfer function of the controller, the transfer function of the plant, which is not known. And of course, here we have a transfer function with respect to the disturbance. Other criteria used in our study are the overshoot, rise time, and the settling time. And these criteria are defined in figure 5. The main results of our paper are represented here in simulation results and comparisons. To control the multi-level inverter, we used in simulation several schemes with P, PI, and PID controllers and different practical tuning methods. And we have 2 simulation cases. We try to assess the control performance for the multi-level inverter with RL load. And here the control goal is to regulate the effective voltage at the inverter output. And the second case is to evaluate the control performance for the inverter with motor load. And in this particular case, the control goal is to regulate the angular speed. In the first case, we provided the voltage feedback loop with a PID controller, and we try to simulate a target with an intermediate circuit voltage of 300 volts. And in this slide, you can see in figure 6 some simulation results. In the left panel, we have the results obtained with the P controller with the Nichols tuning method. And in the right panel, you have the results for the output and the set point, of course, when we used a PI controller with Nichols tuning method. You can see that in the first case, we have a not zero, not null steady state error. And in the second case, when you use the PI controller, we can obtain an almost null steady state error. Of course, the overshoot is bigger in this particular case. In figure 7, we have another set of simulations. In the left, the PI control law with Ziegler-Nichols tuning method, and in the right panel, the PI controller with the Hokushin tuning method. Of course, we have here some slight oscillation, but we cannot assess the quality of the control only by viewing this kind of evolution. So in table 2 and table 3, we computed all these local and global criteria, steady state error, overshoot, rise time, and in the second case, the integral errors. From the analysis of this criteria, it can be concluded that the Nichols tuned PI controller enables the best accuracy performance. And the Ziegler-Nichols PI controller achieves the accuracy performance under the condition of a lower overshoot. But the advantages of integral criteria is that they can capture the behavior of the error through the entire evolution range. And in this case, the PI regulator with Nichols tuning is the best choice. The second case is dedicated to the performance analysis when we use an inverter with motor load. And here the rotational speed feedback loop is provided only with a PI controller, because we observed that the derivative component leads to some oscillatory behavior of the output. And in figure 8, you can see the evolution of the output versus step set point in the case of P controller with Nichols tuning. And in figure 9, you can see the evolution of the output versus reference when we use PI controller with Ziegler-Nichols and with the Hokushin method, respectively. Of course, these are a realistic evolution of the output, because we introduced in the simulation model a lot of realistic elements. From the criteria analysis point of view, in table 4 and 5, you have all the local and global criteria. And the conclusion in this case is that we have a surprisingly good behavior of the P controller with tuning by Nichols method. But from the point of view of global criteria, we obtained the best results with the PI controller with the modified Hokushin tuning method. All these analysis and simulation are just the first stage of the development of the prototype in our project. And here in figure 10, you can see the experimental setup, which is almost ready at the Indial Track company. And now we are in the stage of testing and validation these simulation models on a real environment. And finally, the conclusions. The controllers with better control results are the PI type in both simulation case, and the derivative control components do not give adequate results. For the first case, when we have linear load, we obtain the best results with PI controller with Nichols method, and in the case of motor load, with the PI control low tuned via the modified Hokushin method. These obtained results are realistic because we have nonlinearities, saturations, which are present in the closed loop system. And of course, if it is necessary to obtain a superior performance for this closed loop control system, it is necessary to design more advanced and nonlinear control laws. Further research will target the experimental test with the functional 3-level inverter, which will be characterized by some innovative features. Thank you very much for your attention.
Thank you, dear colleague Salisteanu. Do you have, dear colleagues, any question for Professor Salisteanu? Chat is empty. And we have just time for one more presentation. I have no time to ask, but very interesting. Thank you. Very, very interesting was your presentation, dear Professor. Next presenter.
Thank you very much.
I will introduce. You're welcome. I will introduce next presenter. Next presenter comes from Slovakia, and he is Richard Zelnik. He will present the following paper: snub design for flyback converter. Are you here, dear colleague Zelnik?
Yes, do you hear me?
Yeah, of course.
Thank you.
You're welcome.
Now I share my screen.
Yeah, we're waiting with that.
see you my screen?
Yeah, you shared it with us. Please take your time and present your research results.
So, good afternoon, everybody. My name is Richard Zonik, and I am PhD student at University in Žilina in Slovakia. And at the beginning, I would quickly, So at the beginning, I would quickly go through the points of the presentation that are, and I will present to you the articles number design for flyback converter. The outline of presentation is short, introduction, an application, simulation, practical design, and conclusion. So at first, I say something about the application. The power supply was used in the application for the control system of three-phase inverter system, which provided the power to its control and auxiliary circuits. It has a wide input power supply up to 700 volts. Its task was to power the sensitive electronics, and therefore it was necessary to ensure its proper functionality, which includes the design of protection circuits. And I would say all PWM converters have non-ideal parasitics that lead the ringing waveforms that must be properly suppressed. Without this, semiconductors can be prone to failure and noise levels will be higher than necessary. In this article, we will talk about the practical design techniques for the most commonly used snubber and clamp circuits for the flyback converter. So the article focuses on the practical and efficient design of snubbers and flyback converter topologies. In the first step, we simulated the power part of the converter simulation program in LT-SPICE. The simulation program supports the real models of diodes, transistors, and their parasitic properties. The simulation demonstrates only the effect of leakage inductance on the overvoltage of the primary switching elements, in our case, the MOSFET.
I'm sorry, may I ask you to switch on the camera?
Sorry?
May I ask you to switch on camera?
Oh, okay.
Okay, thank you.
On the left, you can see the effect of leakage inductance on the voltage profile on MOSFET and without the use of snubbers. On the right side, you can see the waveform with the protection circuits used, which will significantly affect the oscillation and overvoltage peaks on the switching elements. Practical design. First of all, it's necessary to analyze the courses of switching element, which consists of three basic voltages. The upper corner shows the right corner shows the real waveform without the use of snubbers and clamping circuits. And below this figure is the composition of the waveform, which consists of VDL, it's DC link voltage, VRO is reflected voltage, and VOS is overshoot voltage caused by leakage inductance. In the first case, it is necessary to design an RC snubber which ensures the reduction of oscillation arising the transistor caused by leakage inductance and parasitic capacitance. Requirements of design: the RC snubber are simple. Choose a resistor to properly dump the ring and select a capacitor and make sure the dissipation of the network is not excessive. For low frequency application can be used decimal boxes, and values are determined empirically, but at higher frequencies, a more analytical approach is needed. As you can see, when calculating the RC snubber, we need to know the frequency of oscillation as shown in the figure on the right, and the leakage inductance of the transformer. Here it is possible to find out in two ways. The first of them is to measure the leakage inductance with an LCR meter by connecting the LCR meter to primary winding of the transformer and shorting all other windings. This we get the measured value of leakage inductance. Subsequently, we use simply formulas to calculate the values of the elements snubber. But if it's not possible to use an LCR meter, we can use a more analytical way to determine the leakage inductance of the transformer. We are primarily interested in the parasitic elements in the circuit, where LLK is total leakage inductance, comprised of PCB trace inductance, Davis packages inductance. Let me see. CLK parasitic capacitance is mainly due to output capacitance of MOSFET. Before we can design the snubber, we must first determine CLK and LLK, as you can see in equation. We could attempt to measure CLK and LK directly, but a more elegant method can be used. For this LC circuit, we know that, as you can see in first equation, where F ring 0 is the frequency of oscillation without a snubber in place. If we edit an extra additional capacitor across transistor, the initial oscillation frequency from F ring 0 to F ring 1, where F ring 0 is less than F ring 1, and resonant frequency will change. So if we measure F ring 0, then add the NOC additional capacitor and measure F ring 1, we can determine CLK and LLK. So following this calculation, we determine snubber resistor, where we can determine the degree of damping of oscillation using the zeta parameter. We calculate the snubber capacitor value as in the previous case. Here I would mention that the measured leakage inductance using the LCR meter was 8.3 microhenry, and the calculated course was 7.8 microhenry. So both of methods are suitable for use. There can see a comparison of waveforms before and after using the RC snubber, where we record a significant reduction in oscillation and also a reduction in overvoltage. The same procedure can be used for the design of the snubber for secondary diodes. Now, primary design primary LCD clamp circuit. In figure, you can see the RCD clamping overvoltage circuit, this blue part, which has the task of eliminating the overvoltage peak on the transistor, which is caused by leakage inductance. The RCD clamping circuit works by absorbing a current flowing through the leakage inductance. As soon as the voltage on the transistor drain reaches the voltage at point X, sum of the DC-link voltage and the capacitor voltage, the diode starts to conduct to limit the overvoltage. We must consider that the capacitor is large enough so that its voltage does not change significantly during one switching cycle. The results of design RCD config circuit. The waveform is measured at the input test voltage of 300 voltage, and there can be seen the limitation of the overvoltage peak, which can be seen on the picture on the right side. In conclusion, the article focuses on the practical design, efficient design of snubbers in flyback converter topologies. It includes a calculation, simulation, and practical verification. To consider two testing methods for detection leakage inductance, and it was a confirmed calculation by measurement on a physical model of the flyback converter. Thank you for your attention.
Thank you very much for your very interesting presentation, dear Mr. Zelnik. Any question for Mr. Zelnik from others? Chat is empty again. One question from my side. Could you please show once again, I think, 5th or 6th slide, where you compared this snubber and without snubber, the first one. Yeah, this, without snubber and this snubber. For instance, you showed the waves with and without snubber. For example, these two figures are so different. Did you say some words about application of this in practice?
Sorry?
About your findings. This solution with the snubber, there we can find it in practice. In which devices?
In which devices? So in a flyback converter, for example.
Is it possible to buy, for example, converter with this snubber? All converters available on the market are without it.
Sorry,
is this originally your finding, or is known before?
This is sorry. Is known before, but it's from more articles. When I designed flyback converter, I know I won't know how to design a snubber, so I find how it say.
For example, this is very useful. Results show that if you decrease level of waveforms on this one, this is very useful. And I believe that manufacturers, if have this, will improve their devices, converters significantly. Okay, that's all.
Thank you.
Any question more for Mr. Zelnik? No questions. I would like now to conclude this session and to say thanks to everybody. You presented very nice papers today, and I believe that our work today was interesting for all listeners. Thank you very much for attendance, and now I'm officially closing the session of Power Electronics. Goodbye.
Thank you, Dardan.